Welcome, Algebra 3. We're in Lesson 30. We're going to talk about the addition of vectors first, and then we'll talk about some more triangle business, I should say. So there are some vocabulary words that you need to add, some definitions. So we have a word called the resultant. And the resultant is what you get when you add vectors together. And in order to add vectors together to get the resultant vector, you have to convert them back into their rectangular coordinate form. Okay, so that's what you get with a resultant. Then there is an equilibrant. Let me put that up here. EQ. That's supposed to be an I. So the equilibrant has the same magnitude as the resultant, but it is 180 degrees different. So that means if we added two vectors together and we got a resultant that was here, the equilibrant would be here on the other side. So 180 degrees different either way. It's just the opposite location on the Cartesian coordinate system, right? So if this is the resultant, this would be the equilibrant. I'm not gonna spell that out because I'm not gonna do a very good job that small. All right, so let's do some problems that ask us about the resultant and the equilibrant, and then we'll practice with those. We need to refresh our skills on adding vectors together anyway, using our new nomenclature of hooded I and hooded J for X and Y. And here's what I use to remember which one is which. You know, once upon a time when we did this, right, let's say that was our vector, and then this was our triangle that we would create. We used R to represent right or left, and if it was positive, it was R, and if it was to this side, it was negative R. Remember that? And this was U for up and down, and if it came this way, it was a negative U. Could be on the negative y-axis, right? Remember that? Well, now we use the proper term, the U and the R, which is to help us remember the difference and put them in the right place. Now we use I. I is going to be your x-axis, and J is your y-axis. The way I remember the difference is that this is the x-axis, and this is the y-axis. Y has a tail, J has a tail, so they go together. X does not have a tail, I does not have a tail, so they go together. And that's how I relate the two in regards to which one gets the I and which one gets the J. The X value gets the I, and the Y value gets the J, because both the Y and the J have tails, and the I and the X do not. Okay, and if you're following along on Jupyter, then you'll notice that I've added that hooded character to your keyboard for Algebra 3. All right, so let's clear this, and we will start with 30.1. So 30.1 asks us, let me turn the page. 30.1 asks us to find the resultants, which just means adding them together. The resultant of 4 and 20 degrees plus 7 and negative 230 degrees. So first we draw our little system just so we can see where everything is located. It makes it easier to have a reference sketch. right? And so we rotate around to 20 degrees, which is going to be about yay right here, right? And then we draw our little line here. This is 4. Let's call this A and let's call this B, just so we can have a point of reference to name them. Actually, you know what? We're not going to do that. We're going to do the actual letters that they require. So this is I and this is J. Okay. So for this vector, let's do this, or this polar coordinate, we'll find the resultant, or we'll find the rectangular coordinate. So we need to find, we've got 20 here, 4 here. So in order to find these, we have to know whether they're the opposite or the adjacent. So in this case, J is going to be the opposite and I is going to be the adjacent. And that helps us a lot because when we write out so, ka, toa, then it helps us find the other, right? So I have my hypotenuse dimension, so I'm probably not going to use toa. I'll use sine and cosine. So to find the opposite, I'll use sine. So that is going to be the sine of 20 is equal to 4. Actually, no. It's equal to j over 4, right? And both of these are positive because this is on the positive side of the x-axis and the positive side of the y-axis. So the sine of 20, I'm going to multiply both sides by 4 for the sake of getting rid of the denominator here. So 4 times the sine of 20 is equal to the j of this rectangular coordinate. So I just pull up my calculator and we do, let me clear this out. We do the 20 sine times 4, and that is 1.368, which rounds to 1.37. So 1.37 is our j coordinate. So now we do our I, we'll use cosine. So we've got cosine of 20, and that would equal the I over 4. But if we multiply both sides by 4, this is what we get. So we pull up our calculator and we clear that and we say 20 cosine times 4 is 3.758. We round that to 3.76. And that is our value for our x, or our I side. That comes first. So our first resultant vector, or not our first resultant vector, our first rectangular coordinate is 3.76 I plus 1.37 J. Okay, so now we do the second one, and the second one is this one. So notice we have a negative 230 degrees. So when we draw this system, we're going to measure the opposite direction. So if we begin here and go this way for positive, we begin here and go this way for negative. So 90, 180, and we need another 50 to get to 230. So that's going to be about right here, right? So that's going to be 50, ... and this is going to be a positive j because it's the y-axis and it's above the x-axis, so it's positive. But this is on the negative side of the x-axis, so this is going to be a negative I. Okay, same thing we did before. We figure out which one's opposite and which one is adjacent. And opposite is j, just like before, and adjacent is the I. So now we do the same exact thing. we look for the sine. Oh, and this is the length or the magnitude of 7. So we look for the sine of 50. And that would equal the opposite over the hypotenuse. So that would be the j over the hypotenuse. We would multiply by the hypotenuse. That would give us 7 times the sine of 50 is equal to j. We pull up our calculator. 50 sine times 7, 5.36. So 5.36 is our j. And then we do the cosine. So it's going to be the same thing. It's going to be 7 times the cosine of 50 is equal to our negative. We have a negative I. So we pull up our calculator, clear that out, and we say 50 cosine times 7 is equal to 4.4995. That's just going to be 4.5. If we rounded just this one up, it would round this one up automatically. So 4.5 is equal to negative I, and just like any other variable, we don't like to see it negative, so we multiply both sides by -1, so it makes a negative 4.5 is our I. All right, so now we can write this as a rectangular coordinate. I get those two mixed up all the time. This is a polar coordinate, which is the same thing as a vector. This is the rectangular coordinate. So negative 4.5 I plus 5.36 j. And now we literally just stack them on top of each other and add them together. So negative 4.5 for the i's and positive 536 for the j's. We draw our line, and then I'm just going to do it on my calculator because it's easier. And I think we're past that point. I mean, you know, seriously. Plus 5.36, 6.73 for our j term. And then let's look at the I term. 3.76 minus 4.5 is negative 0.74. So negative 0.74 for the I. And that's a positive 6. So that's what it looks like. So now what we need to do is convert this into, or back into, our polar coordinate. So we're going to take this and bring it over here and convert it. All right, so now we draw another little system right here, just like that. And we are going to look at our signs here. We have a negative 0.74i. So we would come over here on the x-axis, because that's the I, and say negative 0.74. And then we have a positive 6.73. So that would come all the way up here. And that would be 6.73 because it's on the positive side of the y-axis. And then here is our vector. And we need to find the hypotenuse in order to find the length, and we need to find the degree of measure as well. Okay, so first of all, we are going to remember our SOHCAHTOA. All right, and let's figure out what we need to do in order to do this. So, SO and CA both require that we have a hypotenuse measurement in order to solve it. We can't do that, so we have to rely on TOA this time. So it's going to be the tan of theta, because we don't know what theta is just yet, is going to be the opposite Here's theta. The opposite is 6.73. And because this is a distance, it's not negative. It's never negative. So this is the length is 0.74. So the adjacent side is 0.74. Now we can do the math. The negative only serves to tell us which quadrant it's located in on the x, or where it's located on the x-axis. That's all. That's all it's good for. So 6.73 divided by 0.74 is 9.09. And then that's going to be the tan of theta. So now we have to figure out what that is, what the degree of measure is, by doing the inverse tan. So I'd click my second key and I would hit the inverse tan, and that gives me 83.725. That would round to 83.73. That's the degree of measure of this right here. Okay, so that would mean that theta is 83.73 degrees. Okay, so we did the tan of theta. That was the tan of theta. So that's tan times theta. So to undo that, we hit the inverse tan, and that gave us our degree of measure. All right, so that would be this degree in here. All right, but here's the kicker. That is not the degree of our vector. Remember, our vector starts measuring here. So we have to go all the way around to here. So that means here to here is 180. So we could say 180 minus 83.73 to find that degree of measurement. So that's what we're going to do. We're going to hit it and say 180 minus 83.73 is equal to 96.27. That is our vector degree. All right, hang on. I got to go get something out of the oven. Okay, so this 96.27, that is what goes in here to our polar coordinate, 96.27 degrees. Let me make that where you can actually read it. There we go. So now we have to get the hypotenuse, which is the magnitude or the distance of this vector here. And we can do that by simply doing Pythagorean's theorem. There's a faster way to do it, to set it up, and that would be h, which is the hypotenuse, is equal to the square root of these two, 0.74 squared plus 6.73 squared. So what I want you to notice is that normally we wait until the end to unsquare the h and unsquare this side. We're just doing it from the very beginning. So we have h already by itself. So now h is equal to square root of, and we just plug in our values. And because distance can never be negative, 0.74 squared is 0.5476 plus 6.73 squared. All right, and that's 45.2929. I'm going to add this to that. So plus 0.5476 equals, and now I need to find the square root of that. So that is going to be the square root of that. It could be 6.77. So h is equal to 6.77, and that's what we'd write right here, 6.77. Now, in order to, we just had to find the resultant for this one, right? But you can write this another way. And you can write this as if you measured from here around this way, right? The opposite direction. So all you would have to do in order to find that would be to take negative 180, because we have 90 and 180, right? Negative 90, and then make this a negative 83.73 and subtract it, which is what we did from the beginning. We subtracted it over, where did we do that? Oh, I didn't write it down. Oh, yes, I did. Here it is. We subtracted it from here, from the positive 83.73. So now we keep this, but we change this to a negative 180 to get the opposite, or the other way to say it. So 180 negative minus 83.73. So the other way to write that would be 6.77 and negative 263 point, forgot what that said, 73. So either one of those is correct. Typically, this is the one I want. If the directions say give the negative degree version, then you would put this. Okay. Alrighty then, let's do example 30.2, and it's going to ask us to find the equilibrant of that resultant. So 30.2, I'm going to have to turn the page here. So we have two forces, and the forces that we have here is in pounds. And we have 4 at 50 degrees, a magnitude of 4 at 50 degrees in pounds, and we have a negative 6 at 170 degrees in pounds. And it's applied to an object, and we got to find the equilibrant of the forces. Okay. So, first of all, how do we do the negative 6? That's kind of scary, because we know that this is the vector, it's a length, and a length can never be negative, right? Right. So we'll attack it when we get to it. Let's do the first one first, and that's the 4 and the 50. So we have a length of 4, and 50 degrees is going to live somewhere around in here. And this is 4. And this is 50, and this is our I, and this is our J, right? So now we can use our sine and cosine. So that's going to be for the I is going to equal 4 times the cosine of 50 degrees. And that is going to equal 2.57 according to the book. Let's double check it with our calculator. 50 cosine times 4, 2.57. Book was right. We just have to check it every now and then. So that's going to be 2.57, and that is the I with the hood. All right, so let's do J. J is going to be sine, because it is the opposite side over the hypotenuse. So the J is going to be 4 as a hypotenuse times the sine of 50. And the book has already calculated that for us, but we'll double check it. So that is 50 sine times 4 is 3.06, and the book has the same answer. So we're on the right page, doing it the right way. So that's our rectangular coordinate for this one. Okay, pretty easy to write. We'll do that in a minute. I want to go ahead and do this negative. So here's our system for the second force, and we have a 6, and that looks like 2-degree symbols. Let me rewrite that better. That's a 0 degrees, so 170 degrees. So this would be 180, so I need to back up about 10 degrees. And that would be right about, yay, right there, right? And that would be 6 long. But if it's a -6, then guess what? We flip it to the other side. So instead of this being 10 degrees, this one is now 10 degrees. This is 6 long, and this goes straight up. So that's what you do when you have a negative vector or a negative magnitude here. That hypotenuse length is going to be the opposite side. We move it 180 degrees. We flip it over. And that's because a length can never be negative, so we have to bring it around. So now we have a different degree right here to use. It's going to be because it's below, it's still 10 degrees, but it's going to make this a negative number and this a positive number. Our I here is positive, and our J here is going to be negative because it's below the x-axis. And before, it would have been above, and the I would have been negative and the J would have been positive, but when we flip it, it swaps the signs because it swaps the quadrant. So now we attack this just like we normally would, and we say for the I term that we have a 6 times the cosine of 10 degrees. And that is going to be equal to 10 cosine times 6 is 5.9, and this 8 we're going to round it up, so 5.91. And that is a positive I. For the J term, which is negative, we'll have 6 times the sine of 50 degrees. And that is going to be 50 sine times 6 equals 4.59. That rounds up. Oh, why did I write 50? I am losing my mind. You know what? When I wrote that, I was looking up here instead of over here. That's 10 degrees. Y'all, this over 50 thing is making me bonkers. All right, 10 sine times 6. There we go. Now I have the right answer. 1.04. And that is negative J. All right, so there's that right there. So these are our two rectangular coordinates, and we are going to put them together to create a resultant. So let's do that now. So there's another way. We don't have to stack it. We can just put it together like terms. So we can say 2.57 for the I plus, because this is positive, 5.91, and that's our I term, plus 3.06 minus, because this is negative, 1.04, and that is our J term. That's just another way to do it. It's the same thing as the stacking. It's just a different format. It's just a different way to do it. So you don't have to stack it if you don't want to. And now you can see what you need to do on the calculator a little bit easier. 2.57 plus 5.91. It's 8.48 is our I term. And that's going to be plus because this is a bigger number and it's positive. 3.06 minus 1.04, 2.2 2.02 for the j term. All right, so that is our resultant of combining the two together. Now we can write it in polar form if we desire. And the way to do that is to, first of all, find our hypotenuse by taking the I. We know the I is going to be the x term and the j is going to be the y term. So that's going to be, if this is the x term, this is one of the sides of our right rectangle, or our right triangle, and this is the other side of our right triangle. So we can just use Pythagorean's theorem right with these two dimensions without having to draw our system. So I'm going to do that right here. So the hypotenuse, or in this case, the resultant vector, is going to equal the square root of 8.48 squared plus 2.02 squared. And those are our two terms that we have here. I'm going to go ahead and do those on the calculator. 8.48 squared $71.9104, so 71.9104 plus, and let's find 202 squared. 4.0804. 4.0804. All right, we're going to add those together and get the square root of that. So this one plus the first one, 71.9104, equals that. Let's get the square root of that. 8.717, so it's going to be 8.72. So the resultant vector is 8.72. And now we can find the tangent in order to get the degree of this. And that is going to be the, if you have to draw a reference for this, that's going to be, they're both positive. Both of these numbers are positive, so it's going to be in the first quadrant, right? So that means like this, the j side is going to be the opposite and the I side is going to be the adjacent. So that little sketch will help you figure that out. So this is the j and this is the I. Okay, so the opposite is j and the adjacent is the I. So now we can find the tan of theta, which gives us the degree of measure here, is equal to, it's TOA, so opposite over adjacent, so the j, which is 2.02, over the I, which is 8.48. So now we put that in the calculator. So we get 2.02 divided by 8.48. And now we have to find the degree of measure, so we're going to use the inverse of tan. 13.398, that could be rounded up to 13.4. So that's what we're going to do. So theta is 13.4 degrees. Okay, so we have our resultant magnitude and our degree of measure. So we put that together and we get 8.72 at 13.4 degrees. Okay. And the equilibrant is going to be the opposite of that. So remember when I said the equilibrant is just going to be the opposite? So the equilibrant would actually be, let me get this blue. the equilibrium would be this direction and up like that. So just the opposite of both of these. So the negative and the negative. So we would rewrite the equilibrium as negative 8.48 I minus, sorry, I don't know why I said plus. I knew it was the opposite. Minus 2.02 J. So the equilibrium is just the one on the opposite side of the quadrant from the resultant vector that we came up with. So whenever we would do the calculation, all that's going to be different is that this is a negative number. So negative 8.72, same degree of measure, 3.4. Easy peasy. Okay? All right. Let's see, we have one more of these just to get our heads wrapped around it. $30.3. All right, so here they're throwing us a little bit of a curveball, and it says what vector force must be added to 20 at 30 degrees newtons to get 25 at 0 degree newtons. So basically what we've got to do is we have got to figure out what the rectangular coordinates for 20 at 30 degrees is and what the rectangular coordinate for 25 at 0 degrees is, and find the difference between the two. Instead of adding them together like we've been doing, we're going to find the difference. We're going to subtract them this time. And then that is going to, that force that is the difference, we turn that back into a polar coordinate. Okay? So let's get started. First of all, we'll begin with 20, 30. So I know that 30 degrees is going to be in the upper right quadrant, quadrant 1. So that's going to be about a third of the way. So that's 30 degrees here. This is 20. And here's this. Here's my I, it's positive. Here my J, it's positive. All right. So we are going to do cosine of 30 times 20, and that is going to be the A, because it's ka. Let me write that up here just to make sure. So ka toa. Yes, to find the adjacent, we are going to put the cosine. Yes, cosine is adjacent. So that is going to be the cosine of 20 degrees. I'm sorry, 30 degrees. 20 times the cosine of 30 degrees is equal to the I measurement. $30 cosine times 20. 17.32. I. All right, and now we're going to do the J measurement, and that is going to be the opposite, is the opposite of 30. So that's going to be 20 times the sine of 30, and that's going to be our J measurement, and it's positive. So that is going to be 30 sine times 20, and that could be 10. So 10 J. So there's our initial newtons, or our initial rectangular coordinate for 20 at 30 degrees newtons. So we have 17.32 I plus 10 J. Awesome. All right, now we've got to the other one. So let's do it down here. So at 0 degrees, that's right here. So this is just going to be 25 right here, right? So we have a length of 25 with an adjacent of 0 and a opposite of 0. So 0 and 0. And we have 0 degrees, so it's right up there on that x-axis. So we could say 25 times the cosine of 0 is equal to 0 cosine times 25 is 25. 25 I, and then 25 times the sine of 0 so 0 sine times 25, that's 0. 0 J. All right, so now we have our resulting resultant vector here is going to be, well, not a resultant vector, but our rectangular coordinate that we will add to or subtract to get our resultant vector is going to be 25 I plus 0 J. So now we're going to put those together, or we're going to subtract this one from this one. I think, hang on, let's reread this. What vector force must be added to this to get this? So this is the greater one, this is the smaller one. So we have to figure out the difference by subtracting the second or the first one from the second one, okay? Because something must be added here to this one. So we're going to say the second one, which was 25 I minus the first I, 17.32. There's that I. Plus, and here is the second J. That is going to be 0 minus 10. And that is the J. So let's do the math there. See what we get. 25 minus 17.32 is 7.68 I. And then 0 minus 10 is just negative 10 J. So that's our resultant vector right there. And if we wish, we can put it in polar form and put it back in this system right here. And the way to do that is just to take these, the x and the y, and say r is equal to resultant, or the hypotenuse. It's the hypotenuse there. And it's going to look something like this because we have a positive and a negative here. So this is 7.68, and then this is 10, so it's going to be a little bit longer. So 7.68, and then this is a negative 10, so it just tells us it's 10 long. So we're going to do 7.68 squared plus 10 squared. When we do the math, and we put that in the calculator, 7.68 squared plus 10 squared is equal to something. Hang on. I don't have it calculated for me. 7.68 squared. And we know that 10 squared is 100. So it's 158.9824. 158.9824. And when we get the square root of that, it is 12.61. All right, so 12.61 is going to be our hypotenuse. And our degree is we could go a negative this way. And all we have to do is find the tan. So this would be theta. And that would be the inverse tan of theta, which would be 10 over 7.68, because this is the opposite and this is the adjacent. And when we do the calculation here on our calculator, we get 10 divided by 7.68. And then we do the inverse tan, and we get 52.48 degrees, and it is negative because we're measuring this way. So negative 52.48 degrees. So our resulting vector would be 12.61 negative 52.48 degrees. And that would be in newtons because that was the unit of measure that it was originally given to us in. All right. So this is the polar or the rectangular coordinate. This is the polar coordinate. All right, so let's talk about overlapping triangles and how fun that sounds. All right, in the second part of this lesson, we talk about overlapping triangles, and it's about proofs and how to write those. So in one of our previous proofs in about lesson 15, it told us that sometimes the best thing to do is to separate your shapes, and that way you can see them better. So that's what we're going to do. We're going to take this shape here, this triangle. Oops, not that one. I'm going to take this one. Here we go. I'm going to move him over, and I am going to redraw his points here. This is C, this was A, and this was D. Okay. Now we are told that AB is congruent to DC. So this is AB, and this is DC. We're also told that BD is congruent to CA. So BD is congruent to CA. So those are our givens to start with, right? So now we'll begin at the beginning. I'm just going to take the givens. AB is congruent to DC, and BD is congruent to CA. Those are our givens. Now I'm putting them all in one, but you could put them into two statements. In fact, I'm just going to go ahead. That's what the book has, is two statements. So I'm just going to write it the way the book has it. So those two things are given. Now, we know that these two are the same line, right? So therefore, we can say that these two are congruent because they are the same line. So we can say that AD is congruent to AD, and because they're the same line, that is the reflexive property. And therefore, we have one side, another side, and a third side. So when we have those three things, we know that those triangles are congruent. So ABD is congruent to triangle DCA because of the side, side, side congruency postulate. Easy peasy. That's all that this entire section is about. is separating them so you can see them, or rotating them around to make it easier to look at. So let me put another one up here for us. So here we have, again, overlapping triangles. So if you want, you can undo them, right, to see them better. So that's what I'm going to do. I'm going to redraw PQY. So here is PQ, and there's Y. There we go. So this is Q, Y, and P. And now this is this one is Q, this is X, and this is R. And I'm going to do my givens first. PQ is congruent with RQ, and QY is congruent with QX. All right. So, let's first start with the givens. 1 PQ is congruent to RQ, and 2 QY is congruent to QX. That's a given. That's a given. So we're going to prove that these two are similar triangles. Well, the one thing we know for sure is that Q is the same angle in both. So we can make that a congruent angle for both of these. So number 3 would be that angle Q is congruent to angle Q. Right? So that would be, again, reflexive because it is the same in both. Reflexive property or reflexive axiom is what, because it's a known truth that a thing is equal to itself. So that proves triangle PQY is congruent to triangle RQX because of side-side angle, or we call it side angle side, congruency postulate, however you want to write that. Right? So you see that side angle side, side angle side. Easy peasy. All right, let's do 30.6 and then we will be done with lesson 30. So in 30.6 we have a couple of overlapping triangles. We have a triangle here, we have a triangle here, we have a triangle here, and we have a triangle here. And we are going to have to really pay attention to what we have to prove and what we are given to determine which triangles we need to draw. So we have to prove that XV is congruent to YU. So XV congruent to YU. That's what we have to prove. So let's do that. Let's start with the givens. Well, let's start with looking at which triangles we may need. So XZ is congruent to YZ. XU is congruent to, XV is congruent. That's not congruent, that's perpendicular. XV is perpendicular to YZ, and YU is perpendicular to XZ. So it seems to me that we're using these top two. So that's the ones I'm going to redraw. There's that one, and then there is this one. Okay, so somewhat similar. So we know that XZ, this is X, and this is Z, and this is V. This is U, and this is Z, and this is Y. So right away, XZ is congruent to YZ. And also, because this is perpendicular, this XV, I didn't write that very well. Let me straighten that back up. XV is perpendicular to YZ. That tells me that this is a 90-degree angle here, right here in this corner. And if YU is perpendicular to XZ, then this is a 90-degree angle right here, which means that ZU is also a 90-degree angle. And so those are our givens, right, that we have. So that tells me a lot. So number one, XZ is congruent to YZ, and that's a given. And then number two, I have XV is, actually, no, I'm not going to do that one. The first thing I'm going to do is I'm going to say, after my given, I'm going to expound on this and talk about my 90-degree angle. So XVZ, the measure of angle XVZ, remember the vertex is always in the middle, is equal to 90 degrees, and that is the definition of perpendicular lines. Okay, and then number three, I'm going to do the same thing. I'm going to say the measure of angle ZUY is equal to 90 degrees. That's the definition of perpendicular lines. So therefore, number four, the measure of angle XVZ is, actually, I take measure off because we're going to talk about congruency. So I would just say angle XVZ is congruent to angle ZUY. And that is going to be all right angles are congruent. Okay, so there's that. So now we have Z and Z, and that is the same angle. It's right here at the top. It's the exact same angle on both of those. So we can say angle XZV is congruent to angle UZY, because Z is the vertex in the middle, and that is the reflexive property, because it is the exact same angle. So now I can say that triangle, oh, that's not what I'm trying to prove though, is it? No, I can say that. That's exactly what I want to say. Triangle XZV is congruent to triangle UZY, and that's going to be through angle, side, right? Angle, side, congruency postulate. So angle, side. So that allows me to say then that Did I write that? I did not write that correctly. This should not be a Y. This should be a V. I don't know why I wrote a Y. That allows me to say then that XV and UY, XV is congruent to UY because congruent parts of congruent triangles are congruent. And that is my final answer. Right? And you could also write this as angle, 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 because we know if two angles are similar in two triangles, then all three angles have to be similar. So angle, 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 side congruency postulate is the same as angle, angle, side congruency postulate. One could argue that angle, angle, side is more correct here because we're having to prove that these sides are correct. So anyway, that is 30.6. That is the end of lesson 30. You see, sometimes you kind of have to stretch things out and spread them out in order to see all of the moving parts and figure it out. I would strongly recommend, when it comes to the right angle thing here, whenever you have perpendicular lines, go ahead and mark those before you separate your triangles, because it makes a difference. It impacts what your drawing looks like and helps you to see it better. So mark congruencies. You know, there's a little bit of a trickiness to marking congruencies when you've got a line in between the whole thing. So you don't know where to put the congruency. It's better to put the congruency after you separate the two triangles, because then you can really see, you know, that it's the whole line and not this part of the, you know, from here to here, but it's from here to here. All right. That's all I would say, is be careful when you draw your congruencies so that you make sure you include them in your separated triangles correctly. You don't want to overlook something. And that's all I got. So I will, which is enough because we've been talking for an hour, and quite frankly, I'm getting kind of hungry. So I'm going to go have supper and have fun with those practice problems.